Right, so welcome to this probably 16th lecture um, on random processes, and today we are going to shift to a new module in the course. So I've been drawing this just to let's say have this very clear in your minds what we have been doing. So we started with something uncertain, yes. So uncertainty um, basically including uncertainty in the mathematics or the modeling or the things we do, and just the general description, motivation, all that. And then we went on to what assign probabilities, talk about how to assign them, what kind of functions can contain those, right? So there we work with PDF, CDF, etc., right? um, then we went on to simplify this thing to replace it with moments, etc., right? Make things more manageable. Yeah. After moments, we after doing all this, we went to the random processes in two stages. Yeah. First, we worked with some general definitions or classifications, right? DTS and discrete time, discrete state, all that. Yeah. So some are wide sense stationary or not. So some general classifications. These are by far not the only classifications, but normally in a course you cover the classifications that are important or for the course or relevant for the course, right? So general classifications that we were relevant to us, um, and then what we did was several examples, right, of random processes, several common random processes. So what were the several common random processes that we saw? The random harmonics, right? Moving average, Markov chain, and their relations to random walk, Wiener process, which is Brownian motion, and diffusion processes. And then the last lecture that we did, we went on to point processes. So renewal, Poisson. Yeah. So how are they linked? Quickly कोई बता दो. तीनों. So तीन circle हैं, right? पहले तो ये. One contains the other two, right? So what's the outer circle? Point process, right? What is the requirement? That is, you are counting events that happen randomly. The count you keep at any given time is the point process. This guy. Yes. The count you keep for the number of events in 0 to t. Yeah. And if you allow that t's, the actual events when they occur, t1, t2, whenever they occur, are random, then you are dealing with the point processes. Yes. So how did we go to the special case then here?
Renewable process.
Yeah. What was the requirement?
Independent identity restricted.
What?
Extent.
This what was extent?
The
So
process
the time spacing, the interval, ये कीजिए, yeah?
Yes.
Interval between two events was IID.
Yes.
Yes. So whenever there is event T1 occurring, T2 occurring, then there is T3 occurring, and T4 occurring, then T5. This interval each time is a random variable. We call it xn. Yeah. All these intervals which are random variables, if they are independent of each other, if this interval somehow depends on the past, any of them, then this is no longer the renewal process. Yeah, linear process, we require this to be independent of each other and identically distributed, meaning coming from the same distribution with same parameters. So if one of these is coming from Gaussian, then all are coming from Gaussian with same mean and variance. Yeah. If one of them is from Gaussian, other is from uniform distribution, again the condition for the definition of linear process is violated. Again, you might say, why are we putting these conditions? Are actually very realistic, and as I said in the very beginning, why do we classify? It's a divide and conquer rule. Why do you work with linearizations and linear systems? Because usually they are easier to work with, and then you can try to generalize, right? So that's where we got to the renewal processes. Now, what took us to, so this was the IID assumption on intervals, right? Then what took us to Poisson?
Identically distributed.
वो तो हो गया.
Exponential.
Exponential.
It's
So,
difference.
as I said, they have to come from the same distribution. If that same distribution happens to be exponential distribution, then you're talking about Poisson process. So this is another way of defining a Poisson process. And the name, why the name Poisson? If the distribution of these intervals is exponential, it can be proven that if this is happening, events are happening with intervals that are exponentially distributed and are independent, because that condition is also there, then the count will always be a Poisson. It will follow the Poisson distribution. Whatever symbol you want to use. Yeah, I think usually they are P or IS or something. Right. So uncertainty. So some containing the uncertainty in some functions. Then working with something fixed, mostly mean. Now a Gaussian distributed random variable has a mean mu x, let's say. The random variable itself can take many values randomly from the Gaussian, but the mean is fixed. Yeah. So for variables, yeah. So we went from uncertain to fixed, and then we just used all that information to talk about random processes. Some of these we talked about, are they Whiteson stationary or not, are they discrete time, discrete state, all that. Yeah. But now we are going to go back to this thing and ask ourselves this important problem. And the next thing relates to both the random process and moments. Okay. So we are going to look at the realistic problem or situation where you don't really have the full statistics of the process available. All you have is data. Okay. So in many real situations that happens. I mentioned that before. So let's look at that. Let's look at that problem first, and then I'll draw the thing. But this new module is basically estimation. Okay, अब जो नया शुरू हो रहा है अब काम. After this, we are at estimation, and this is a broad, huge field. Inference theory, all that पूरा subject होता है inference का कई होते हैं. So estimation and detection theory, all that fits. This is kind of start of that. In this course, you will see a lot of getting started things. Yeah. So, but if you pay attention, really, this is what you learn here is mostly what you need to get into the field. It sets the foundations. Yeah. So, but estimation of what? Estimation can be of many things. We will focus on the estimation of moments. Now, why estimate the moments and what happens when you go into estimation? We will see that in some detail. For let's first develop this requirement that why do we need to go into estimation. So any thoughts? I've already mentioned it, I think, but if you repeat it, you will maybe will be clearer in your mind. Why estimate the means? What is the other option? To calculate from the formula, right? So let's say there is a random process. Yeah, we start with this random process. It has some values here. Some random process, collection of random variables. Yeah. Now, each of these random variables can have a mean. Yes. We simply just write that as ex1 or exn, and of course, without putting if we haven't put any other restriction, there is no requirement for the means to be same. We haven't put that restriction. So, how do you calculate the mean of this random variable inside the random process? So you have a formula. By the formula, what does the formula say? Says that see the sample space of this guy. Yes, let's say its sample space contains x11 up to, let's say, it has 4 possible values.
The relative distributions.
Times there, yes, p x11 up to yeah, you're saying that you know the exact sample space and you know the exact distributions, yes, values, and then what you can do, sum them up, yeah, all these, and that is the definition of expected value, isn't it? It says it's if it is 1, then it's x1I summation x1I probability x1 I equals for all I, basically whatever the sample space requires. Yeah, or it could be an integration if this is a continuous thing. Yeah, so we're not going into that. You can imagine whichever you want to require, but overall this is how you would calculate the exact moment, right? Okay, same thing you can do for this guy, right? Let's say it has some set of values from its sample space. We're not saying they have to come from the same sample space or anything, right? So this guy will have its own sample space, and for each one you will need that information, the whole thing. Yeah. Now as I said, unless the process is stationary, of course there is no requirement for these to be the means to be same. Okay, now what happens is this requirement, which is theoretically very nice, to look at a process, know its whole sample space, and then really know the distribution assignment, the PDF or the CDF for the each value in the sample space, or have the function. It's very nice, and if you can have it, very good. But real life problems are usually not like that. Okay, in real life problems are mostly not tossing a coin or throwing dice. Yes, they are about data coming in, signals coming in, process randomness in the process happening a lot. So there it becomes rather hard to say that, okay, now first tell me the whole sample space and tell me the whole distribution, and then any computer can just, even with the calculator you can try to do that. Yeah. So yes, theoretical is nice, but in reality we are often dealing with not this theoretically nice thing. We are dealing with observations of the random process, measurements, data collected. Yeah. Neural networks, what do? They are working with observations. They tell a neural network, these are a million pictures of different bicycles. Okay, send them through it, and it learns and learns and learns. When it is done, when they send it a picture that was not in the million, it is either a bicycle or not, and then is it a bicycle, and it says yes or no with some confidence score.
ChatGPT working is something.
ChatGPT is a neural network. It is based on neural network and other AI. Yeah, um, probably different vector machines, and so neural network is a part of AI. Then there are other um, members in the AI family. Yeah. So uh, so the real life is most often not really like this, that you can get the whole sample space and that thing. So then this leads to this issue of trying to then estimate these moments, right? You could try to estimate the density itself. Sometimes we do that, but remember what I said, in real applications we mostly don't work with the density, we work with the moments, first, second. Very rarely we go to third moment. Yeah. So if you're just gonna work with the moments, why estimate the whole distribution, which is going to be harder? Why not just estimate the first two moments? Yeah. No, the issue with estimating is what? Estimation itself introduces randomness. ठीक है, आपका estimate, your estimate of what grade or marks you will get in the course, yeah, maybe this thought. For the same situation, different people may estimate the thing differently, right? So political parties usually estimate that 1 billion people will come to their whatever they are holding, their rally. Yeah. So but their opponents say nobody will come, so estimates can vary, there is randomness in the estimates. So then the issue is, now it seems that we are back to randomness. We started with uncertainty, so random process. This is uncertainty was there. Yeah, we went to moments, also PDF we did. So, and these were fixed. If you know the mean and variance of a Gaussian random variable, then the distribution is fixed. Yeah, it's not, the distribution isn't randomly changing. So these were fixed, and what we did so far were theoretical definitions, which are nice, of course. This is where you should begin, that is fine. They were theoretical definitions what we did so far. Yeah, write the whole nice definition. Now comes the issue that we don't actually have the whole sample spaces and whole nice this thing to get the PDF, or unless you just say it's crossing a coin, or in some cases you can, but mostly it's data driven. So then what you need to do, you need to estimate. Often we put a hat to represent that this is not the true value. It could be, so your estimate might be so perfect that it always gives the exact same values, fine, but otherwise we are saying that this is an estimate of the PDF, and then you have to estimate the moments, and these are now, as I said, estimates. What is the thing here? They are not fixed, and there is uncertainty, some uncertainty in there. So from uncertainty to back to uncertainty. So this seems a bit useless, but actually it is still going to help, because without the definitions, trying to estimate is also hard. You need to be able to say something about what you're estimating. But more importantly, if your estimates are good, then the uncertainty will be less than the uncertainty there was originally. Yeah. So let's see today in today's lecture, basically, we will see, okay, if you are going to estimate, when is an estimate possible, for example, how to find it, and what is a good estimate. Okay, you can always make an estimate. That
When
is
the
not an issue.
moments and periods are fixed, then how they are random and how you estimate this? The, when you say
Yeah.
that they are fixed, then what kind of estimations mean in that case?
Yeah, so theoretically they are fixed, right? They are there. But if you don't have access to, let's say, if you had access to this information, you could find the moment, right? Now let's say I tell you that I don't have access to this. All I can do is repeat this process a million times and then give you a million values of x1, a million values of x2, and million values of x3. Yeah. Now, if you know that this is tossing a coin, you can again go back. So it's fine. I don't need million values. I can theoretically do it. Again, you will be here. But just think that I don't know what the process is, or it's the process, the physics under it, the thermal noise in our electronics. The physics under it is so complicated. I cannot go in and model each thing. Same thing with Brownian motion. Remember? That if you can tell me the exact initial condition of all the atoms and molecules, and then you could run a simulator to chart the exact path, but that's where we started. One of the issues with uncertainty, or where it came from, was that getting the precise knowledge may not be actually impossible, but may be extremely unfeasible. Yeah. So then in that case, if I haven't told you, or I don't know exactly, or I know that the physics under it is extremely complicated, it's not just tossing a coin, you cannot talk about it theoretically. All I can give you is, let's say, repetitions, 10,000 million repetitions of this process. Yeah. Then what is the mean variance, or the PDF? We do try to estimate PDF sometimes, but mostly it's these guys we are interested in. Then the question is, now, if you estimate or guess the mean of this guy based on a million values, no other information, yeah, how close would you be exactly getting the same which you would have gotten theoretically, or not? What are the properties of processes that will in some cases require just 10 values to get a good estimate, for others you will need a million values? All those things we have to try to do. This is what we do in inference theory, in estimation theory, right? There is a problem. This is the problem. We only have access to realizations, or recordings, measurements of that process. We may have some physics, some statistics available. If you have all of it available, yeah, okay, as we've been doing so far, just find the exact value, fine. But in most applications, that is not the case. Okay, so for example, the when you talk on your mobile phone, you call your friend now. Do you know where your friend is? So the signal that has to go to your friend through different towers, and then through different environment, the temperature, the materials here, kitni सारी, so much variation in there. Are you able to even define the sample space of that noise? Let's say वो एक noise add हो रहा है ना, आप उसकी sample space कर सकते हैं आप, पागल हो जाएंगे right? So all you can do is try to find different instances, try to model or collect a lot of data. As I said, the neural network even takes away a lot of this estimation theory. It automates that thing. It says, just give me a million pictures of bicycles, not the same bicycle, because then it's not trained on enough variation. Yeah, a million pictures of different bicycles, and I'll tell you the next picture you give me after those, is it a bicycle or not? Yeah, वो फिर अगला level आ गया, वो उसमें कमाल ही कर दिया. But this is this is the foundation of all that. estimation. So we will learn in this module how to find the estimates. This is just a motivation, and the issue involved that I've already mentioned, there will be uncertainty. Yeah. So again, I showed you very quickly last time. I can repeat that diagram. Let's say you are estimating the mean. Yeah. So most cases your estimate of the mean, if you are doing a good job, will be the true mean, which should have been, plus some, let's say some delta, some variation, yeah, some amount that you are off from the true mean, and this itself will be a random variable now, which makes the whole thing a random variable. If your estimate is good, ideally, let's say this is Gaussian distributed, then ideally your estimator's mean value should be the true one, and the spread should be very low. That means you're mostly close to the true value. We will come back to that, but um, that will help us try to talk about, say, when is an estimate good. Yeah, we want to precisely define what is a good estimate. You could estimate things all the time. So if you're going to plan a wedding or walima and you are asked to estimate how many guests, so one estimate would be that the guests will be less than 7 billion. Because that's the number of people in the world. Yeah, guess तो है ना ये, this is an estimate. हो गया estimate. Is it useful? Is it good? इसमें variance नहीं है by the way, yeah, so it's not varying very much, so in that sense it looks good. You always say yes, 7 billion से कम लोग आएंगे, शर्तिया लिखवा लें. But is it useful? So what are the properties, what is the criteria or the set of some rules that tell us when is an estimator good? General ones.
Error is small.
Yeah, but in what sense? So we will see that. Yeah, because we're talking about random variable here. Yeah, so it's not just one error. Yeah, it's gonna be a set of errors. So then, what should be small? We will come to that. Yeah, you can think about it.
You just say the maximum of in that set, the error set will be very small. Then I say that is a good estimate.
Okay, so if the maximum is very small and it occurs 90% of the time, the maximum error is very small but it occurs 90% of the time. And now compare that to another estimator whose maximum is slightly bigger than this one but only shows up 10% of the time. Then which one is better? We're talking about randomness, yeah, random thing. So maximum is small, okay, but it shows up so much that its worth becomes too much. So you are often off by, let's say, 2, a value of 2, yeah, or 4, and that offset happens 90% of the time. Compare that to you being off by 6 at most, but that happening only 1% of the time, and mostly you are off by 1 or 2. Then this first one isn't a good idea, right? So we will come to that. But what I'm mentioning here now is that this is what we will do in the estimation module. Yeah. Now the the thing what we need to establish actually is, mathematicians before finding a solution often they find what? Does the solution exist?
Yes.
Right? So there is a joke that I think there is some room and there is some puzzle in there, and first an engineer goes in and he goes in and solves it and comes back, and then they just randomize it again, and then a mathematician goes in, keeps looking at it, and then comes out without doing anything. And they asked him why, and he said, I just saw that a solution exists. I don't need to solve it. So first you need to say, does a solution exist? When is this estimation possible? There will be situations where or a lot of the estimation methods that we will develop will not apply, will not be possible. So first we have to establish when is that estimation possible, and therein comes in a very important concept of ergodicity. Okay, अब बता ergodic plus now, means no. So white and stationary was one thing, and then there is this new thing, yeah, ergodicity, ergodic processes. When is a process ergodic, and why does that matter, right? For estimation theory, at least for estimation, the ergodicity has direct link with justifying a lot of methods that we use in estimation. When the ergodicity fails, the huge class of estimation approaches become useless. Then we have non-ergodic estimation process things which become very complicated. It's like going from linear to non-linear, basically, yeah, in a way. So this was more of a trailer of what's coming. So estimation is often needed. Reality is not so nice as throwing a dice. Okay, we don't even know the whole sample space, let alone assign. याद है Kolmogorov, if you're gonna meet the axioms, you cannot miss any value in the sample space, because then all your assignments will be wrong, because all the assignments have to sum to 1, right? तो वो तो फिर गलत है. आप बाकी सबको देख रहे हैं, दो sample you miss them and you gave one probability to the sum of all the remaining ones, तो वो सब गलत हो गया. So and we also try to see, okay, what is a good estimator, all that, but before that we say, okay, in what situation estimators can be obtained based on observation, what kind of observation is needed, and that's where the concept of ergodicity plays a role, at least in our context, right? So let's say we have a random process x1, x2, x3, yeah. Let's say this random process is made up of is a collection of 3 random variables, yeah. And let's say that we observe lots of realizations. Suppose I don't know the underlying distribution here. I don't know, is it throwing a dice or what, or if I know it's coming from a thermal noise, it's a Brownian thing. I know, okay, this is the physics, but it's so hard to model that basically I don't know, yeah. So the assumption is I don't know the underlying distribution here, yeah. In most cases I don't even know the sample space. I may have limits on the sample space, but I don't know exactly what value is in there. Is it continuous or what? So then how can I estimate the mean and variance of this thing?
So will the random variable, we just know कि ये random variable और same family से आ रहे हैं या नहीं आ रहे, इतना हमें मालूम होगा या फिर ये भी नहीं मालूम होगा.
Let's say we start with this, that we don't know that either. Okay, so let's start with the general thing. So how can we then try to get this? क्या approach हो सकती है? फंस गए ना अब हम वो basically. Now you do that every day basically. When you do find average of 10 numbers, what do? You add the 10 numbers, divide them by 10. Yeah, because you say, okay, I don't know any. You didn't give me any other information what these numbers are. Well, best I can do is take an arithmetic mean, apply equal probability to all of them. That's it. So that is one thing you do, but that's not the only thing. Yeah. So let's say if we observe lots of realizations of these random variables. So let's say we observe them and we see that x1 x2, x3, it turns out to be that x1 has, let's say, some values, x2 has some other values, x3 has some other values, and we observe that if, let's say, when we observe these several realizations, we find that sometimes it's like this, sometimes it's like this, sometimes it's like this, sometimes it's like this. You can imagine all the different ways that this can play out. Yeah. So this goes here, all that. Yeah, lots of different, these are all the different, lots of different lengths. We don't say all of them because I mean, we don't know anything about this, right? But let's say you measure or collect a lot of realizations of this process. Let's say you have collected m realizations of this process. Yeah. So if you have collected m realizations of this process, I can write what you saw for the first variable in the first realization, what you saw for the second variable in the first realization, and what you saw, I'm giving them these names, small x3. Yeah, I've already drawn that. Yeah, and so on, and I have taken m realizations, so x1m, x2m, that is the value the second random variable took in the mth realization. Yeah, and x3m. Okay, from here can you try to say something about the statistics or estimate the mean of these random variables? Does something come to mind, some trick or something? Let's say this guy has two values, alpha and beta. Yeah, two, what you observed was always these alpha and beta, and depending on how many times they appear here, that's fine. Can you take a guess of what we can do? Of course, if you knew that it always only takes alpha and beta, and you knew exactly what PDF alpha has and what PDF beta value has, you could just find the mean of x3, right? That would have been the calculation base, that alpha probability alpha plus beta probability beta. Yeah, if you also knew that this was the only sample space, that's it, you could get the exact value. Now you don't have it. Yeah, what can you do now? This is not available. So would it be a good idea, or would it make sense to maybe say, okay, I cannot find the true one, I could try to estimate it as the arithmetic mean? और कुछ है नहीं ना? Yeah, so summation x3, is it, yeah, I is 1 to m divided by
I
m
summation
divided by m.
summation of
हाँ वो mth value है ना, capital M. So there are m values, m realizations. Yeah, we observed m realizations. Yeah, okay. So does this make sense, or does this come close to this? What we are essentially saying is that, let's say, since you have already observed that if you found that this thing took only two values, alpha and beta, then all of these are either alpha or beta, right? That's one thing. That's what you observed. We're not saying that we knew it from the start. This is what you observed. They were either alpha or either beta. So let's say k alpha of them were alpha and k beta of them were beta, such that k alpha plus k beta is capital M. Yes? So then essentially what are you saying here? We are saying this is k alpha, right, times K alpha times or alpha times K alpha plus beta times K beta divided by M. Yes, and now you have kind of brought this thing in here, the relative frequency or the relative likelihood. What is the relative likelihood of K of alpha showing up? It's K alpha. Let's say K alpha, if M is 1000 and K alpha is 500, then the 500 by 1000 is half. 50% of the time K alpha was showing. Yes. Now, why is this an estimate still? Looks like it should be, but why is it still an estimate? Because we based it on observation. We didn't really have the exact um, sample space or the distributions, yeah, or the density functions. So it seems to make sense based on the observation.
So we don't have an exact sample space, but what we are doing, we are just making an estimation. This could be our sample space, or what in estimation?
No, we don't have the sample space. Yes, we are saying the realization are so many that um, the all the possible values will show up. Okay, meaning becoming the sample space, and they will show up with their relative frequencies, which are their probability. Right? Do it like let's say you don't know that tossing a coin gives 50-50, or throwing a die gives uniform distribution with mean 3.5. Okay, let's say we don't know that, but we could roll the die 10,000 times, put the values, and you will still get the mean around close to 3.5. Yes, so that is what's happening here. We are saying there are enough realizations. We will talk about this, that M has to be very large or large enough. Large enough, what is large enough? That also has to be made precise or discussed. But let's say that it's a million, billion, just go so high. Let's say we can go so high. Then we are saying that these are realizations so many that firstly all the possible values will show up, meaning that it will give us an image of its sample space. Second, there are so many that the relative frequency of occurrence would reflect their likelihood. तभी वो आएंगे ना, एक चीज बहुत likely है तो वो that will show up much more than the other, right? The only thing is that since we haven't started with the theoretical thing, we cannot call it the true mean or true variance or true PDF. It is still an estimate, yeah, and it can be wrong. You know, if you try throwing a coin, let's say 100 times, you could end up with not 50-50. थोड़ा सा ऊपर नीचे हो जाता है ना, 100 दफ़ा फेंक के देख लें आप, you'll be very lucky to get 50-50, 49-51. अब आपका mean value क्या है? अगर if you assign -1 to a head and +1 to a tail, and you do it without going into the maths, without calculating here, try 100 coins, toss try कर ले, आपका mean पता है कि zero नहीं आ रहा होगा, असल में zero ही होना चाहिए ना in this situation. It won't be zero. Sometimes it's 0.001, sometimes it's minus 0.001, sometimes it's, and that is the delta I was talking about, random thing, yeah. So the reason I talked about this here is that if you take this approach, this you are doing what we call the ensemble average. Ensemble average or ensemble mean, and this one was done for x3. Similarly, you can try to get the ensemble. This approach is called the ensemble average. This is an important term because this will come back when we define ergodicity. this term will be used. So if you don't understand it now, you'll have a hard time understanding ergodicity. If you use this approach, you take lots of realizations and then base your estimate on the values that you saw in the realizations. That approach is called ensemble average. Now, what's the other average then? That we will go. So, although not for this random variable, but or it could be this one. Let's say in another strategy could be that you observe one very long realization of a random process. Okay, so one thing is to say, okay, I will throw 1,000 coins at the same time. That's one way. Another is to say, okay, I will throw or throw a coin 1,000 times. Yeah. So not always possible, but in many situations you are able to get one long realization of the same random process. So what you are able to do is say, okay, we will observe n values of the random process. So we will say, okay, x1, x2, x3, x4 and so on, xn, and we say, okay, in this one realization it took x1 value here, then it took x2 value here, then it took x3 value here, x4 value here, and so on. x5 value here, and let's say x6 value, x5, so xn value here. This is one long realization of a random process. Okay. Now, another strategy to get the mean might be that you say, okay, I will take an arithmetic mean or average of this thing. Okay. So then what are you doing? You are saying, okay, now my estimate of the mean is going to be summation x I is 1 to n divided by n. Okay. This will be similar to tossing a coin 1,000 times. What we discussed previously was throwing 1,000 coins at the same time and seeing, okay, how many are heads and how many are tails. So this kind of approach, when it is possible, we call it time average.
It's for the one time, if you want to see this, for one realization.
It's a one realization, but the process is such that it allows you to take that realization for a long time. Okay, so for example, you are measuring some thermal noise in a sensor or something, yeah, or it could be Brownian motion, for example. The thing is that one approach would be to do this, that you observe, let's say, 100 or 1,000 different pollen grains, yes, each one going, yeah, in the same circumstances, yeah. So different realizations. Or you could set up, so let's start with that. So what we did previously was taking the ensemble averages. Another way is to let one of them go on, right? Let it continue in time and take the average like this. Now I'm not saying that two averages will be the same. That's the key thing. You might already think, okay, how is it that the averages you get here and the average you get through this, how is it that they have to be same? No, that is where ergodicity comes in actually. When they are same, the process is ergodic and estimation becomes easier. When they are not same, the process is non-ergodic and estimation becomes really hard. Okay, so I will come to that. But for now, I'm just giving you this definition, the uh, time average versus the ensemble average. So in this case, now you have another estimate which is based on n. Now the question is, would the second strategy work? Firstly, why do we want to go to the second strategy? It seems simpler, right? 1000 coins फेंकने से बेहतर नहीं लगता कि एक को 1000 दफा कर ले. Yeah. So it seems simpler. If it works, it's very nice. Yeah. Now one condition of course is very obvious for this to work. कोई आप यहाँ से guess कर सकते हैं what is that condition for this time average idea to work? Now see, the ensemble averages are average here, whatever values you will get. Yeah, they are not one value. They're not required to be one value. But the time average is just one value. How can one value represent so many different averages? So it seems in general it's not the same. Time average is not the same as ensemble. But where can it be the same for mean? There is a special subclass of random processes for where at least it is possible to have it. Wide sense stationary. If this process was wide sense stationary, remember all these means will be same. All the means would be same. If all the means are same, then at least there is hope for one value to represent them all. Yeah, but if they're all different, there is no hope for one value to represent them. Because हो ही नहीं सकता ना, वो there are 10 different means. Yes, and you are saying I will represent them with one value. How is that possible? It is possible if the process happens to be wide sense stationary. Again, we are not saying that as soon as the process is wide sense stationary, the two become equal. We are saying yes, at least there is hope. Yeah, that it is possible for the time average to represent the ensemble average. So, what else is required? Or let's try to see. Overall, what is it that is required for our estimates to work? So I will give you two examples. Based on those examples, this was general. Yeah. Now I will try to start with rolling a die, and we will see this thing happening. ये थोड़ा सा टाइम लेता है ये.
ensemble एवरेज जो हमने पहले पढ़ा था, अब आप ये हमने ये पढ़ा था कि एक पॉइंट के ऊपर हम डिफरेंट रियलाइजेशंस देख रहे हैं क्योंकि क्या प्रोबेबिलिटी है हमारे पास. यहाँ पर आई गेस आप ये कहना चाहिए कि इंटरवल्स के ऊपर शायद शॉर्ट इंटरवल पे देख रहे हैं. मतलब
इन टाइम एवरेज,
ensemble
एवरेज तो वही था ना.
एक पॉइंट के ऊपर हम तमाम वैल्यूज को देख रहे हैं ना, मतलब एक टाइम के ऊपर
at the same. So you freeze the time, but then you have different
kind of
realizations. Yeah. Whereas in the time average, you are allowed to go on in the time.
Then how said they are not represented by a same number? It's similar like when time is extended for one realization. तो वो भी तो हमारे पास एक ensemble average का सबका sum करके हम divide करें तो एक ही number आता है.
Yes, so you get one number in ensemble average. That's the thing. In ensemble average, you're not required to get one number. For example, the first example that I had drawn, if you remember, this one, yeah, alpha beta. This guy may have this is the ensemble average, right, of x1, the ensemble average of x2, ensemble average of x3. This example most likely the three averages are different. I mean, there is no need for them to be same. Yeah. Now, imagine if you were to replace this by, let's say, you could observe this process happening over and over time. Yeah. So then you got some realizations, all the different realizations of that. But if the process extends in time and then you try to find the average like that, yeah, then that average will be just one value, whereas here you have three different values. I'll show you, this will come now with the dice example also. It may be a bit difficult to absorb at first. Let's think of it like this again. One way to think of it is comparing, throwing, as I said, 100 coins. Compare that to throwing 100 times one time. Compare that to throwing one coin, and that is actually ergodic. In that case, the two means are the same. But there are. I will show you an example now where the two will not be the same. Okay, that will show you. Okay, don't just assume that if I could take 1,000 realizations of this and then get their means, and instead of that just repeat this thing 1,000 times and get the mean. Don't think that they're always the same. From tossing a coin, it looks like that, but because that is ergodic actually. We will see that. But let's see. Let's say we have. I'll do example 1, which will give us an idea of what is going on. Let's say you throw a single die, okay, single die, and define a random process Zn such that Zn is the number that shows on first throw. Okay, so Zn equals, we could also say Zn equals omega, where omega is the number that shows on the first throw. Okay, so then how do realizations of such a process look? Let's see. So if you do it the first time, firstly, what is Z1, Z2, Z3, Z4, this random sequence, yeah, it can go on, right? Okay, now can you tell me what the realizations of this would look like? It's a bit tricky, it's not straightforward. So firstly, let's maybe put these here. What are the possible values? Yeah. Firstly, we can see that, yeah. These are the possible values. It's throwing a die. The first variable Z1, yeah. What value can it take?
All of 6.
All 6 of them?
Yes.
Let's say in one realization, take one. Which one?
4.
4. So let's say it took this. What can Z2 take?
1.
No, read that carefully. Zn is equals this number that shows in the first. So
All
in this realization,
4.
what should it be?
4.
4 again. Yes? And this realization, as soon as you lock the first one in the realization, it should look like this, yeah? Now think of another realization. करें कोई और realization. क्या होगी?
2
2 होगा तो क्या होगा? 2 ही चलता जाएगा.
जी.
अब जितनी दफ़ा मर्जी this process can go on to infinity. The way we define this, just to give you the idea of what can happen. The way you defined it, it's basically its realizations look like these, right? So now what is the ensemble mean in this case at each time? The ensemble mean, how would you draw it? So in this case, now these are the realizations, right? Agreed?
Ensemble. Yes.
Realizations are this thing, yeah, basically straight lines. Okay, that's fine. But the ensemble mean would be, for the first one, it's the mean of these, which should be 3.5.
3.5.
Right? So that is fine. What about the second one?
3.1.
3.5. Yeah. So at least it seems that this is more or less stationary in the mean. The mean isn't changing. Yes? 3.5. Okay. This is what we will call the ensemble mean. Now think about the time mean.
Oh, it will not be the same for one.
कोई भी पकड़ लें इसमें से आप take one realization and go through as far as you want. There is no way you will get the same mean, right? That's the trick with the realizations, that what you want with time averages. You're saying I'm going to work with just one realization. It's going to be very long, and then I'm going to hope that the statistics I get from here represents the statistics of the whole thing. Okay, firstly we said it's impossible if the process is not stationary, because then even the mean is changing. One mean will never represent all 10 values, or right? But even in a situation where it's not changing, the mean is not changing, still one realization will never give you, in this is an example here. It is to show that there are situations where the time average, which is based on taking, just observing, you just log yourself to one realization, keep observing it, and then use that to find the mean or the other statistics. अब ये तो mean देगा 1. If you had gotten hold of this realization, you would conclude that the mean is 6. If you had gotten, and if you say okay, let's get hold of all the realizations, then you're going back to ensemble. आप ये भी कहते हैं ना कि I could make all of them very long and then get hold of all of them, then you're back to ensemble averages. That's fine. Of course ensemble averages are fine, but ensemble is also a headache often to get. So in this case it seems that one single realization is not a good representative of the situation. Now let's change this experiment into example 2, which is what you are mostly familiar with, and in example 2 I'm going to say that Zn, there is a sequence Zn such that or let's call it Xn to keep it different from our Z guy. Xn, sequence of random variables within a random process, Xn such that Xn equals omega n, and omega n is number that shows on nth throw. This is different now. Previous one we logged it to the first throw. Yeah. So now what do the realizations look like of X? This guy. So you are throwing it right again and again. First throw, second throw, just like here. You had several throws X, but here the of the value was just logged to the first throw. So X3, X4, and so on. Yeah. Now what do the realizations look like? Firstly, of course, it makes sense that the values, you shouldn't see anything, even if you don't know the sample space of this experiment, you shouldn't see any value other than this. Dice कहाँ से देगा? Yeah, okay. Unless आपको dots पढ़ने नहीं आते. Yeah. So what do the realization look like? Let's start with one. Let's say first one कोई value ले, whichever. So 2. Okay. The second can be
This is different.
right, because it's saying the and it's toss. So second toss.
Yes, sir.
Yeah,
It
so
can be 2, 3, 4, 5, 6. Yes.
any of those.
Any of those.
Yes, and then this guy can be any of these, and this guy can be any of these, and maybe again like so. So this is one realization, but you can easily imagine that from the 6 things that can occur, so what do your realization look like? Maybe another one starts here, goes here, goes here, goes here, goes here. Another one goes like this, then goes there, and over here, and here. Another one may be like this. Yeah, वही काफी सारी, lots of them happening. Yeah. Now in this case, what's the ensemble mean? Again, this is the ensemble mean, right? And you should find it to be 3.5, or at least expect it to be 3.5, and it's stationary. The mean is stationary, doesn't change. 3.5, 3. What happens in this case if I take one realization? Remember now, one realization, let's say I take one of these, I take any one of them. Let's say I take this realization and I follow it over time. Yeah, so this realization, this is one realization, वही जो हमने यहाँ से शुरू ही थी, then it keeps going, right? It keeps going. Now what do you think the time average would be if this realization is long enough? Guess क्या है आपको? पिछले में तो we knew that the time realization was going to be 1, 2, 3, 4, 5 or 6, depending on which realization you got hold of. Yeah. Here it seems whichever realization you start with, whichever you take hold of, this one, whichever, it's fine. As long as it goes long enough, the mean should be 3.5.
Mean should be 3.5.
होगा ना? क्यों?
Okay. Because we have infinite possibilities and infinite possibilities to come with 6, with 5, with 4. So we have same possibilities to come up with 6, 5, 4, 3.
Right,
so
right,
right.
right. So firstly, I will say this, that in the first case we saw that the ensemble mean was not the same as, or we didn't calculate exactly, yeah, but common sense we could see that it won't be the same as time mean. Whereas in this example, it seems that the two might be the same, so ensemble mean is the same as time mean. That's one thing. Second, as you said, and other than infinite thing, the main idea now, that is what is required for a process to have this thing. Basically, I'll say that in simple words, but then we can we'll make it more precise later. You have heard of Three Musketeers? Movie भी नहीं देखी? Okay. Alexander Dumas's famous novel of three fighters. There are actually four, but the three ones are the main. Anyway, so there are many movies on that, but novel purana hai. It's a classic novel, Three Musketeers. There's like we have knights or ninjas in Japan or UK. So the French had musketeers, special fighters जो sword से fight करते थे. They had a motto in the novel: one for all and all for one. मजे का model, yeah, that one for all, one will work for all the group, yeah, and all will work for each one in the group. Yeah, this is more like a unity thing with contribution from everyone. All for one for all and all for one. I like to think of this thing actually doing that. When, in general, when is a process such that its ensemble statistics, in this case the mean or general statistics, would be the same as the time mean, when it has this general property that one realization can represent the whole statistics. Yeah, here one realization did not represent the whole possibilities, whole set of possibilities, right? It was just sticking to one of them, not one for all. This guy seems to be covering, if it goes on, ये सब में आ जाएगा बार बार, yeah, it will represent the whole statistics. Another way to say is that all for one, that all these, the statistics of all these is encompassed in one of them. Yes, only then, this is more a generic thinking thing. Yeah, then it seems that you will end up with ensemble mean, ensemble variance, ensemble PDF, let's say, being equal to time statistics. Yeah, so ensemble statistics being equal to time statistics.
That is called ergodic.
Yeah, then it is ergodic. Okay. The completely ergodic process is when the whole statistics, meaning the entire PDF, ensemble PDF, is equal to time PDF. It's completely ergodic. But as usual, it's very hard to prove or work with. And since we know that we are only bothering about mean and variance and covariance, let's say, so we talk about ensemble in the mean, ergodic in the mean, ergodic in variance. Okay, so we stay to first two. We say, okay, since we are going to work with these two, just let's prove that the process is ergodic with respect to these two, and then all our results will hold. Yeah, so yes, you're right. A process where this thing happens is what we call the ergodicity, and it actually has to be a subclass of stationary processes. You saw that even if the mean wasn't constant, there was no hope to talk about this thing. Yeah, so basically these are stationary processes, and in them there is this class of ergodic processes. Then there are stationary processes, they are not ergodic, like the one I just showed you, the first example. At least what we saw in the mean was stationary, wasn't it? But the process ensemble mean was not the same as the time mean. So the process fell here, whereas this process falls here. This is stationary and it is ergodic. Now, general ergodicity, let's define that. What is general ergodicity? The most general definition, like stationarity, what was the general stationarity? Not the wide sense. General stationarity, what was it? The whole statistics, meaning the whole PDF or the family of PDFs, should not change with time. Then we said, oh, too much. We went to wide sense stationary, talking about first and second one. Same thing we'll do here. First we'll talk about the general ergodicity. So an RP, so let's say general ergodicity is a stationary random process. It is inside stationarity, for which I'm just trying to write a basic definition. Ensemble statistics, all the ensembles. So if you can show PDF, then it covers all the statistics. Yeah, is the same as time statistics. Okay, then we say this process is ergodic, just ergodic, meaning just like stationarity, it means it's the most general version. Yeah, but as we saw, we are often interested only in the first two moments, so we will say okay, we can also talk about, instead of this, we could talk about ergodic in the mean. That is when ensemble mean equals time mean. Okay. Then it is ergodic in the mean. Then there is ergodic in covariance. Okay, when the, and then you can imagine in ergodic in higher orders. Yeah. Of course, if you show this, then this will follow. If the PDF is ensemble PDF is same as time, then all the others will follow because they come from, all the moments come from the PDF. Right? That will follow, of course, but it's too hard. So we go to the things that we want to work with: first moment and the second, the mean and the covariance, because we are talking about processes. Just variance is not enough for us when we go into processes, right? So that is in some in the mean and that. Now I will not do the exact definition of the ensemble mean time, this ergodic in the mean, not this lecture, but in the next lecture, because we actually need to define some laws that will help us put this mathematically, this thing. Okay, that those laws are some of them, the law of large numbers, the weak and strong laws. Basically we need those, which will help us say when it converges in probability, converges in the absolute sense, that we will need. But just to close this off, I just want you to have another interesting interpretation of the ergodicity, which is what I like to say, population versus the individual. Okay, so in general, when entire population statistical behavior is same as the individuals, that's what we said in realizations, but now I want to say it in general thing. If the population's behavior is same as the individuals, right, then the process is ergodic. Like for example, here I'll give you two examples. I'm not going to take very long because not much to draw, right? So it's just one is, let's say there is a population. So this is the population versus individual interpretation of ergodicity. So population, let's say, is throw 1,000 coins. So the 1,000 coins are a population. Yes, if you throw 1,000 coin, reduce the frequencies, let's say reduce frequencies of head and tail. Individual is take one coin, throw one coin 1,000 times. Individual, this is population. Reduce frequency of H and T. Do you expect them to be same or not?
Same.
This case may seems will same. So whenever you expect, of course we will write the exact mathematics of ergodic in the mean, but it sometimes helps to have a general feeling of, am I dealing with something linear, non-linear, stationary, non-stationary, like that. So it often helps to try to formulate the problem differently and say, okay, is the population behavior same as the individual? Now let's do this one, another one, without actually doing anything. Let's say you want to find what is the most popular picnic spot in Islamabad. Okay, population would be observe 1,000 families, in Islamabad, right? So observe 1,000 families to see which spot they like to go to. Yeah. Another thing is, this is so see, mostly they which free picnic spot they go to. Sorry. Then the other thing is, observe one family
In different spots.
for, let's say, 20 years. Okay. So this is population behavior. This is individual behavior. If you conclude based on this which picnic spot is most popular in Islamabad, and if you try to conclude based on this, would you get the same or not? You see one family इस weekend ये उधर गए थे, इस weekend ये इस्लामाबाद में ही है family, right? It was one family over 20 years. You observe them. Do you expect to find the same picnic spot or
सेम ही होना चाहिए इसका भी।
सेम नहीं होना चाहिए,
same?
नहीं होना चाहिए,
आपका क्या हाल है?
नहीं होना चाहिए।
Same होना चाहिए?
नहीं होना चाहिए।
नहीं होना चाहिए ना?
Yes.
Maybe this family is very reserved, निकलते ही ना हो घर से,
Yes,
20
sir.
साल घर ही बैठे रहे। Yeah, maybe they always go to the same spot,
Yes, sir.
right? This is, you won't end up with the same statistics like favorite, the same behavior. I'm just saying a picnic spot, but it can be any other thing. Yeah, so could be same, but you don't expect it to be, right? Because individual families may have their own preferences. उसको 20 साल तक आप देखते रहे वो हमेशा एक ही जगह जाए, जो maybe they like this water park something more than anything else. So over 20 years, 90% of the time they go to the water park. Does that mean that the population as a whole goes to water park 90% of the time, right? So in this case, it seems that the individual behavior and the population behavior are not the same. Yeah, and in fact, human behavior is highly non-ergodic. Okay, and that affects stock markets, and that's why stock markets are so hard to estimate the future or predict the future, because a lot of depends on the sentiment and so many things. So in general, human behavior is extremely non-ergodic. There could be families that never go out. फिर क्या करेंगे उसको picnic spot का, yeah. So with that, I close the general development of the concept of ergodicity. Okay, I took some time developing it in different ways, but because I felt that when I discuss with students or even sometimes not students, graduates, I feel their concept of ergodicity is not very clear. So that's why I developed it in 2 or 3 different ways. And remember, why did we go there in the first place? We had to estimate the statistics based on observation. Then we said, okay, is it enough to go for one observation for a long time, which will be very nice if we could do that, or do we have to get lots of population and then do it? Yes. If the first one is possible, then estimation becomes easy. Okay, and from here on, whatever we develop for estimators or thing, they will be for the ergodic case. Okay, and actually a lot of processes are actually ergodic, but yeah, human behavior, stock market, many others are not, and then you have to find other solutions. Okay, thank you.